Welcome back, everybody. In this video segment, we will cover section 7.2 in our textbook, Trigonometric Integrals. Trigonometric Integrals. In this section, we cover a couple of sets of integrals, two sets of integrals. The first involves integrals of powers of sine and cosine. And the way our textbook illustrates that in the general form is we're looking at integrating sine to the nth power of x times cosine to the nth power of x dx. Okay, where m and n are assumed to be whole numbers. We've solved some of them, specifically if for example, m is 0, you have the sine goes away and n is 1, you're integrating cosine, and the integral of cosine is sine. If m and n were both 1, you have sine times cosine. You could make a u substitution from Calc 1. Real easy integral there. So the idea is to look at evaluating every possible case. And it turns out that there aren't that many cases possible. In fact, there are only 3 cases possible, and they all make a lot of sense. So there's not really that much to memorize. So let's dig in. Before we dig into the section, though, I want to let you know that you're going to see a lot of trigonometry coming back here, and this goes for from now to the end of the course. While you are responsible for knowing a lot of trig, and specifically knowing those trig identities that you learned in the trig class, and I think there's something like 75 or 80 of them, you don't have to go out and rememorize them. As we go through different problems, and as you go through different problems and homework and stuff, you'll realize that you'll need to look back at some trig identities and stuff. So what I think I'll do, and I'm saying this to make a note to myself, I will post, if I can find it, a list of trig identities on Canvas. Okay, so let's get started. Let's look at breaking this down into this set of integrals, powers of sine and cosine, into 3 cases. Let's take a look at what we'll call case 1. I think your author calls this also case 1. Case 1 is where n is an odd number, an odd power. Let's take a look at a specific case. Let's take a look at the case, let's say, sine squared x. So m, as in Mary, is even, cosine cubed x. So there's where n is. N equals 3. Now the whole idea with this case, and actually with the next case as well, is with the odd power, borrow one power and put that next to the dx. Write that next to the dx. So I'm going to borrow 1 from 3. That leaves me cosine squared times that borrowed power. I'm going to lock into the dx, or lock in near the dx. I'm going to group it with the dx. And then the next step is very simple. Think of a u substitution that would give me du equals cosine x dx. I want u so that du is cosine dx. And the answer is u equals sine, and that's what we do. If the power of cosine is odd, you borrow 1, put it near the dx, put that extra power next to the dx, the first power next to dx, and that u equals sort of the opposite function, let u equal sine. Okay, so that's our key. So let u equal the sine function, sine x, and of course then du equals cosine. And we notice we have a little problem. If u equals sine, go back to the integrals, sine squared, that's u squared, but we have cosine squared left over there. Well, this is where the trig starts coming back. We also know that sine squared plus cosine squared equals 1. It's probably one of the most important identities from all of trig. That's really kind of an opinion there, but it's my opinion. I've taught trig for 35 years, 30 of those years here at Cerritos. And I think that this is, if not the most important trig identity, it's way, way up there. Okay, so sine squared plus cosine squared equals 1. Well, I could use this identity and then solve for cosine squared to get cosine squared equals 1 minus sine squared. Okay, and remember that was the problem with our integral, is we had u equals sine, which is fine, that gives us sine squared, and cosine squared, that wasn't in terms of u, but cosine squared equals 1 minus sine squared times cosine x dx. Then make the u substitution, just separating off the other stuff. So u equals sine, so this is u, becomes u squared, times 1 minus u squared, and cosine x dx, that's du. Oops, that's du. So then this is simply integrating powers of u. If you distribute the power, you get u squared minus u to the 4th, integrating with respect to u, and the integral is simple from there. The integral of u squared is 1/3 u cubed. Antiderivative of u to the 4th is 1/5 u to the 5th, plus a constant. U was sine of x, so this is 1/3 sine cubed x minus 1/5 cosine. Oh, no, I keep doing that. The substitution was sine for u, so 1/5 sine to the 5th x plus a constant. Okay, so we don't get too far away from what we just did. If n is odd, that means if the power of cosine is odd, borrow one power from that odd power, put that first power next to the dx, and then that u equals sine. So let's take a look at case 2. Case 1 was when the cosine was odd, so case 2 is when the sine is odd, and it's just as simple. Case 2 is m is odd. The power of sine is odd. So suppose we had, for example, sine to the 5th power cosine squared x dx. Okay, so borrow 1 from the sine. Borrow 1 from the sine. You get sine 4th x cosine squared x. Oops. Times that borrowed power of sine x dx. Lock that borrowed first power with the dx. Then what do you think we let u equal? To get dx equals close to sine of x, let u equal cosine x. Du is almost there. Du is negative sine x dx, so that sine x dx equals negative du. And then make the substitution if you can right away. If u equals cosine, well, we can't quite make the substitution yet because we have that sine to the 4th, but sine to the 4th is sine squared, and we have the cosine squared times the sine of x. And then that sine squared that's being squared is 1 minus cosine squared. By that same identity, sine squared plus cosine squared equals 1. I think I have a little extra x in there too. Yeah, I do. Gone. Perfect. Almost perfect. Cosine squared x sine x dx. Now we can pop the substitution into the integral. So u is cosine. So you're looking at 1 minus u squared u squared. And not quite du, but negative du. And again, one of the simplest kinds of integrals happens or arises or results. It's just powers. Let's expand. Expand the powers. 1 minus u squared quantity squared is 1 minus 2u squared plus u to the fourth. You can verify that if you want by the FOIL method, if you're so inclined. And then finally distribute the u squared and the -1 as a factor from du. And you're looking at negative u squared plus 2u to the fourth plus, let's see, minus u to the sixth du. I'm just double checking to make sure that's okay. It looks just fine. So the resulting integral becomes -1/3. We're just integrating power. -1/3 u to the third, -1/3 u cubed, plus 2/5 u to the fifth power, minus 1/7 u to the seventh power, plus a constant. U is equal to cosine, so we substitute that back in, and it's over. So this is -1/3 cosine cubed x plus 2/5 cosine to the fifth x minus 1/7 cosine to the seventh x plus a constant. So the bottom line with these first two cases is when you have an odd power, borrow one from the power, put it next to the dx, and then let u equal the opposite trig function. Now, so what if they're both odd? Well, if they're both odd, it doesn't make any difference whether you treat it as case 1 or case 2. If it was, let's say, oh gosh, the easiest odd power is 1. First power, sine x cosine x. They're both to the first. Okay, so since cosine is odd power, lock it next to the dx and let u equal sine. I guess this is the simplest possible case, huh? Du equals cosine x dx. Then this becomes u du. Antiderivative of u with respect to u is 1/2 u squared plus a constant. So 1/2 sine squared x plus a constant. Well, then that brings up the idea or the possibility that we might get two different answers. Suppose I treat it as the sine is the odd power. Remember, they're both odd here. In which case I could put the sine next to the dx, and then let u equal cosine. And I'm going to get something that's going to look like a different answer. Oops. So this is the case where both m and n are odd. It's nothing really to worry too much about. You choose which one you want to borrow the odd power from. So if u equals cosine, du equals negative sine. So sine of x dx equals negative du. Our integral becomes u is cosine this time. Sine of x is negative du. And you get negative 1/2 u squared. U is cosine. Cosine squared x plus a constant. And we get an answer. But it looks different. It looks different. It looks different. What's going on? I'm trying to draw. I'm trying to be dramatic here. I'm trying to draw a little triangle with it. Trying to make up a symbol for, they're different. I guess I could have just written different. They're not different. They appear different, but one can be made to look like the other. So let's take the first one. Or the second one. Let's say negative 1/2 cosine squared x plus a constant. Instead of calling it a constant c, I'm going to call it c sub 1. You'll see why in a minute. Well, cosine squared is 1 minus sine squared. Cosine squared is 1 minus sine squared plus the c1 that I have there. Now, if you distribute the negative 1/2, you get negative 1/2 plus 1/2 sine squared plus C1. And maybe bring the 1/2 sine squared but first, plus C1 minus 1/2. Lump those two together, the C1 and minus 1/2. Look at the original answer on the left-hand side. 1/2 sine squared x plus c. Well, replace C1 minus 1/2 with a new constant c. They're the same. They're both correct. They're the same function by identities. So this brings up an important point about homework. And this will happen. Almost guaranteed. You're going to get answers, and they're likely to be right answers, but they're going to look different from the back of the book sometimes, the solutions in the back. Don't panic. All you have to do, if you want to make sure your answer is the same as the author's answer, is you can either force your answer to look like his or his answer to look like yours. That's not the first thing I would try. Or you could go to desmos.com and graph both. Graph your answer and graph his answer without the constant of integration. And if they're just vertical translations of one another, then they're the same thing. Remember, antiderivatives, the only thing that antiderivatives vary by are the constant. And varying by a constant graphically means they're just shifted up and down from one another. So bottom line, here's if you didn't get that. Suppose your answer looks like this, the red. Then you take the author's answer, put it in Desmos, and suppose it looks like that. I wanted it to look like the same thing. Suppose you get it to look like that. Well, then there's almost 100% chance that you're correct. That's a joke. There's a 100% chance that you're just fine. Because the answer, 1/2, in this case, let's say 1/2 sine squared x plus a constant. And this one, the green one, would be like negative 1/2 cosine squared x plus another constant. They are the same function. They are the same set of antiderivatives. Okay. Now, on the other hand, if you get, and this was supposed to be, let's say, your answer, book answer. Now, on the other hand, if you get something that looks like this, and the author's answer looks like this, then there's something wrong. Either the author's wrong or you're wrong. And it's most likely going to be you, because this is the 8th edition of the textbook, and a lot of the wrong answers initially from the initial editions have been flushed out and stuff. But it's possible for there to be a wrong answer in the back, or two. Okay, so let's take a look at, I lost track of where we were. We were looking at the case, where the case where, both cases where one of the trig functions is odd. Now let's suppose we look at the last possible case for this set of integrals. So case 3. Case 3. We're still looking at the same set of integrals. The integrals aren't changing. The form is still sine mx cosine nx to the n power x dx. So the last case, what's left? Cases 1 and 2 cover m even or n even, m odd or n odd. What's the only thing left? Well, either there are only two possibilities. Either one of them, m and n, are odd, or they're what? Or they're both what? So the last case is m and n are even. Well, if m and n are even, we're going to need some identities. We're going to need some identities. We're going to need a few more after this for the next integrals. We're going to have to use what are called power-reducing formulas. The power-reducing formulas we're going to need are sine squared x equals 1/2 times 1 minus cosine of 2x, and cosine squared x equals 1/2 times 1 plus cosine 2x. Standard power-reducing formulas. Why are they called power-reducing formulas? We'll look on the left-hand side of each identity. have sine squared or cosine squared. The power is 2 on the left. And on the right, the angle is doubled, but the trig function is reduced to the first power, cosine of 2x in both cases. So let's take a look at one example. Let's take a look at the case, let's say, well, the simplest case I can imagine. They're both even, sine squared, cosine squared. Okay. So the idea is to reduce the powers. Now this, again, this has to be if both powers are even. So the powers are 0, 2, 4, 6, 8, 10, 12, etc., etc. So the idea is to use the power reducing formulas to reduce the powers to first power. So specifically sine squared x is 1/2 minus cosine of 2x. And cosine squared x is 1/2 times 1 plus cosine 2x. And you go forward with that. The 1/2 times 1/2 is 1/4, can be factored out of the integral. For this particular simple case, we can multiply the 1 minus cosine times 1 plus cosine and get the difference of squares. So 1 minus cosine 2x times 1 minus cosine 2x is 1 minus cosine squared 2x, not 1 minus cosine squared 4x, or 4x squared, okay? And in this case, we could either go forward and use the power reducing formula for cosine again, or we could remember that 1 minus cosine squared of an angle is sine squared of the same angle. Well, that was pretty nice. Doesn't always turn out to be this compact or concise. So again, we're going to use the power reducing formula that says sine squared x equals 1/2 times 1 minus cosine of 2x. But it's not x that we have as the angle, it's 2x. So on the left hand side, see the little green identity? It's not sine squared x, it's sine squared 2x. So I'm going to replace x with 2x on both sides. Well, if on the right hand side I put, instead of x I put 2x, there's a 2 in the formula, but I'm replacing x with 2x. So what's that going to leave for the angle on the right hand side? Of course it's going to leave 4x. The power reducing formula doubles the angle on the left hand side and puts that double of the angle on the right hand side. So this becomes 1/4 times the integral of 1/2 times 1 minus cosine of 4x. Okay, then it's pretty much over. You can distribute, or you can factor out the 1/2, and integration of first powers of trig function is very, very simple. The integral of 1 with respect to x is x, and the integral of cosine of 4x is 1/4 sine 4x. If you need to stop the video and confirm that the integral has that 1/4, that's fine. If you do, then use a u substitution on cosine of 4x to be u equals 4x. Okay, and I put a dx in there that shouldn't be. Let me get rid of that. Always complaining that my students do that, and then I do it. So plus a constant. Okay, so if both the powers are even, you reduce to first powers by using power reducing formulas. Okay. Okay, so integrating powers of sine and cosine is relatively easy. That idea is relatively easy. We've saved the best for last. It was basically a joke. We've actually saved the most complicated integral for last. I want to look at powers of secant and tangent. The way your author writes the general case is tangent m, mth power, secant nth power. Now we're going to need at least 5 things from either trig or calculus, okay? So I'm going to write those things we're going to need. We're going to need a bunch of stuff. We're going to need an identity from trig that says 1 plus tangent squared is secant squared. There's also the corresponding identity 1 plus cotangent squared equals cosecant squared. But we need this one for our case. We need, from Calc 1, the derivative of tangent. Do you remember? Derivative of tangent is secant squared. We're going to need the derivative of secant from Calc 1 is secant x times tangent x. We're going to need something from earlier in our course, I think from last week. We're going to need the integral of tangent. And the integral of tangent is, and we did this in an earlier lecture, is the log of the absolute value of secant. Okay, so if that's, I think we did this when we talked about the section on ln, natural logarithms. So yeah, that was section 6.2 star, I think. Okay, you might want to look that up, how to integrate the tangent. I'll say it out loud. You turn tangent into sine over cosine and let u equal cosine. I'll let you review the details if you want. We're going to need one more integral that's not easy to derive. This is one of the only integrals that I would suggest, complicated integrals, that you actually memorize. It's not a simple task to integrate this. It's not that hard, but it's easiest just to memorize that the integral of secant of x is the natural log of secant x plus tangent x. If you're interested in how it's done, you can check out the textbook in this section, section 7.2. Your author does this as an example. I won't ask you to integrate the secant of x. If you end up with an integral that breaks down into the secant x, you simply reuse the formula, this formula, okay? Okay, so back to our problem. Back to the integral of tangent m power, oof, I'm getting sloppy here. Oops. Tangent mx secant nx dx. Okay, I want to write a little chart for the possible cases. I want you to see this little chart. Cases. Let's say m and n. And the first case we're going to look at takes care of two possibilities. That'll make sense in a second. This first case is m. N is, the first case is n, as in Nancy, n is even. So n, and I'm using E for even and O for odd. So n is even. So we could have that n is even and m is even, or n is even and m is odd. This is case 1. Okay. Case 2 is m as in Mary is odd. This is case 2, in which case you could have n as in Nancy even, and this overlaps from case 1, and that's okay. Or m is odd and n is odd. There's only one case left. Oops, what, I'm doing this in red. So what's the only, if you can think of it, what's the only case left? We have EE, OE, and OO. The only possible case left is where the first one, m, is even and n is odd. And that last case is the most time-consuming and difficult one. But even it isn't that bad if you just approach all this stuff systematically and logically. It's really, really not that bad. So let's go through these. Let's go through these to finish up our section. Okay, we're going to look at specific examples of these things. So let's take a look at the first case. Let's take a look at case 1. Case 1. Let's take a look at, let's say, both even. E, M even, N even. So simplest possibility there, or one of the simplest possibilities, tangent squared x secant squared x dx. You could do this with Calc 1. In fact, you can do a lot of these integrals with Calculus 1. What would you do to integrate this? Well, if you let u equal one of these two, either secant, not the squared, but either just secant or tangent, then du pops right out. Which one is it? If you let u equal tangent of x, then du is secant squared x dx. And this works out beautifully. If u equals tangent, so you're looking at u squared, and the remaining portion, secant squared x dx, that's du. This is a simple case. This is a simple example in this case. So this is 1/3 u cubed plus a constant, 1/3 tangent cubed x plus a constant. So that wasn't so bad. Let's start numbering these. So still under case 1. So we're looking at case 1. Let's take a look at another case. Let's look at the case where, well, let's make the powers, one of the powers at least a little bigger. Let's look at tangent squared. That doesn't look like a squared. Let's look at tangent squared times secant, let's say to the 4th. I claim that it's still u equals tangent x, because du would be secant squared. Well, we have secant to the 4th. Well, remember when we borrowed powers for sines and cosines? Same thing. Secant 4th x is secant squared x. Take the secant squared that you borrowed and lock it next to the dx, and let u equal tangent. This is still the case, E, both even. Well, if u equals tangent, I'm looking at u squared, secant squared. What am I going to do with secant squared? Well, one of those things that I said that we need to remember is that 1 plus tangent squared x equals secant squared x. This is one of the identities we're going to need. So secant squared x, 1 plus tangent squared is secant squared x. So that secant squared x is simply 1 plus tangent squared. So this becomes tangent squared. Remember, we're letting u equal tangent ultimately. So this is tangent squared. 1 plus tangent squared is secant squared. So 1 plus tangent squared times secant squared. Then we make this the full substitution. This is u squared, u is tangent, 1 plus u squared du. And it looks almost like the power of sines and cosines. We're just looking at powers of u. Not quite the same thing. Not the same thing at all, actually, because the u's are not sines and cosines anymore. So this is 1/3 u cubed plus 1/5 u to the 5th plus a constant. The substitution was u equals tangent. Put that back in. Tangent cubed x plus 1/5 tangent to the 5th x plus a constant. Okay, so way back up in our chart, case 1. In case 1, where the power of the secant is even, you let u equal tangent. Okay. Let's look at one more before we move on to the next case. Let's look at one more before we move to the next case. Let's look at case C, part C. Tangent cubed x, secant squared x dx. Tangent cubed, secant squared. This is the case odd for the first, even for the second. It's still even for the second. It's just the first one's odd now. I still claim that u equals tangent du equals secant squared. Make the substitution. In this case, it's direct. It's very simple. So this becomes u cubed du. My goodness, that's so simple. This is 1/4 u to the 4th plus a constant, or 1/4 tangent to the 4th x plus a constant. Okay. Okay, so let's take a look at our next problem. So what I did first, though, is I moved our chart down a little bit so we can refer to it again. What I'd like to do is consider case 2. Case 1 was the power of secant n. The power of secant n was even. Now let's take a look where the power m of tangent is odd. And notice there's overlap. Okay, so I want to consider an overlap case. We just looked at the case, part C of this example, odd, even in case 1. Now let's look at that same example, but let's look at it through another new pair of sunglasses. Let's take a look at it from the point of view of case 2. Strange analogy there. So D. I want to look at the same case, tangent cubed, secant squared. Tangent cubed, secant squared. But now I want to consider this as case 2. So revisit as case 2, odd, even. Okay, case 1 says I could let u equal tangent, and du equals secant squared. It's a real simple integral. Now for considering this as a case 2, I want to do something different. I want to take the odd power. In case 2, both sub cases have the m is odd, and in both cases, what you do to handle this as a case 2 is you borrow 1 from that odd power. So borrow 1 from that odd power, so you have tangent squared. Borrow 1 also from the secant to the first, and put those borrowed powers, secant x, tangent x, next to the dx. Lump them together with parentheses. So what do you think we let u equal? I want to let u equal something so that du equals secant tangent. So u needs to be secant, and du equals secant tangent. And this is one of the things I reminded us about earlier before the lecture really got started. Then make the substitution. This becomes, well, it's u equals, I can't do it right away because I have tangent squared. I need u to be secant. Well, remember, 1 plus tangent squared x is secant squared x. So tangent squared x is secant squared x minus 1. If I take that little green identity on the right and I solve for tangent squared, I get secant squared x minus 1. Then times that kind of isolated secant, then times secant x tangent x dx. Then make the substitution. Make the substitution. It works out beautifully. We get u squared minus 1. Secant is u, so times u, and secant tangent is du. Simple power. A lot of these reduced to just powers. It's kind of nice. These powers are so simple to integrate. So this becomes 1/4 u to the 4th minus 1/2 u squared plus a constant, and it's over. Make the substitution back in. 1/4 secant squared. Oops, 1/4 secant to the 4th minus 1/2 secant squared plus a constant of integration. And compare the two answers. The problems were the same, but we were looking at them from different points of view. Tangent cubed secant squared was 1/4 tangent to the 4th, or this business, 1/4 secant 4th x minus 1/2 secant squared x. If it were me, I'd rather consider this as the previous case, but this can be done this way. So what if you do it one way again and your author does it the other way for the answer in the back of the book? Put them both in Desmos and see if they're vertical translations. If they're vertical translations, your answer versus author's answer, almost 100% chance that you're just fine, okay? Okay, let's take a look at one more before we move to the most complicated case. Let's take a look at where they're both odd. They're both odd. Let's see, both odd. Let's take a look at tangent cubed, secant cubed. So part E. Tangent cubed, secant cubed. Okay. So what did we do in the last example? In the last example, we let u equal secant. In fact, this is what we do for all of case 2. Let u equal secant x. Okay. So in order to make that work out for us, remember both powers here are odd, looking at odd and odd within case 2. Borrow 1 from the tangent, borrow 1 from the secant, take those borrowed powers of secant and tangent and lump them together as a factor with the dx, and let u equal tangent. U equals secant. Gives us du equals secant tangent. Secant x tangent x dx. Make any adjustments using an identity so that we can let u equal secant. Remember, tangent squared is secant squared minus 1 times secant squared times secant x tangent x. Make the substitution. U equals secant, u squared minus 1. U equals secant, secant squared, u squared. Du equals secant tangent, du. Once again, powers of u, which are so simple to deal with. So this is 1/5 u to the 5th minus 1/3 u cubed. U is equal to secant x, so we finish this off. So this is, I'll put it over here, this is 1/5 secant to the 5th x minus 1/3 secant to the 3rd x plus a constant. Okay. Okay. Now let's dig into that last case, case 3. Case 3 above. Case 3. Case 3, m is even. The first is even, and the second is odd. The power on secant is odd, but on tangent's even. The simplest case that I can look at or imagine that would really illustrate this method is where m, the power on tangent, is 0. 0 is still even, and n is 3. secant cubed. This is sort of a classic case. Classic in the sense that I think a lot of instructors use this one and do this one in class with good reason. It gets the job done really nice. Now, this one's rough. That's the bad news. The good news is that this whole case 3, m is even, n is odd, works the same way. First, when m is even and n is odd in this case, reduce the integral to powers of secant. Reduce the integrals to powers of secant. Okay, this has been done for us. I've done that for us here. So if you had tangent squared, secant cubed, you would replace the tangent squared with secant squared minus 1 and reduce to powers of secant. I'll rewrite that in our answer, in our chart later. Reduce to powers of secant. So once we have powers of secant, what do? We're going to use integration by parts in kind of a sneaky way here. We're going to replace, or we're going to rewrite, rather, secant cubed as secant times secant squared. Okay, now I hope you had a chance to look at your integration by parts homework, because a little experience would go a long way here to see why this is working out. Even if you haven't finished this is okay. So the idea then is to let you can't use the Liate device on this. It doesn't work. Liate had logarithms, inverse trig, algebraic, which means powers, trig functions. It doesn't really work out here because they're both trig functions, secant and secant squared, and e exponents. So the key is not so much to let u equal secant, but the key is to definitely make sure that dv equals secant squared. So if whatever the power of secant is that we're looking at, you want dv to be secant squared. And the reason for that is the integral of secant squared is tangent. And then find du. Du equals secant x tangent x dx. And then dig into the integration by parts formula. It's u times v tangent x minus the integral of v du of v secant x times du. So secant x times tangent squared x. And then use that same identity we've been using frequently. 1 plus tangent squared is secant squared, to rewrite that integral in terms of only secants. So this is secant x tangent x minus the integral of secant x times secant squared x minus 1. Then keep going. So this is secant x tangent x. Now I'm going to split this integral that's left into two integrals. I'm going to split this integral that's left into two separate integrals. So secant x tangent x minus the integral of secant cubed, which I get by distributing secant cubed x dx plus the integral of secant x dx. Now, when I distribute, keep in mind that I also have this minus to keep an eye on. That's why the signs are the way they are. Now we've seen this trick before. We saw it in our last section. We're looking at the integral of secant cubed on both sides. So get all the secant integrals of secant cubed on one side. You have integral of secant cubed already there on the left-hand side. You add another one from the other side, you get two of them. Integral secant cubed plus integral secant cubed is 2 times the integral secant cubed. So this is secant x, tangent x. And the integral of secant is one of the ones we memorize. The integral, you may have forgotten. You've probably only seen it once the time I showed you. So the integral of secant, just the integral of secant, is log of absolute secant plus tangent. We can save the constant until the end. So divide both sides by 2. Secant cubed, integral of secant cubed, divide both sides by 2, or multiply by 1/2. You have 1/2 secant x tangent x plus the natural log of the absolute value of secant x plus tangent x. Tack on our constant of integration. So this is as hard as it gets. So when you have the case m is even and n is odd, you reduce to powers of secant, and then you apply this technique of integration by parts. Okay. And that ends this section. That ends this section 7.2. Go ahead and dig into homework whenever you get a chance. And I'm looking forward to talking with all of you again soon.